trapped in the dark. Is it daytime or night? I can't tell them apart. I almost gave up till the loud voice said unto me, you're a child of the King, the great Master is He, who will keep you from falling and suffer defeat if you call on Him on your greatest time of need. Alpha and Omega, the beginning and the end, the bright and morning star. You are never too far.
Good day. Sessions on acids and bases. So this is a November 2022 acids and bases question. Then in the following videos, we will look at 2021, 2020, 2019, 2018, only the acids and bases. So let's look at this question. It's question 7 in your paper 2. So the question says, the ethanoic acid is a weak acid that reacts with water according to the following balanced equation. So this is an ethanoic acid. It reacts with water, and then there is a product of the solution on your right hand side. Yeah, so let's look at question 1, which is question 7.1.1. They said define an acid in terms of Lorentz-Bronsted theory. Define an acid in terms of Lorentz-Bronsted theory. So that was 7.1.1. So Lorentz-Bronsted said an acid is a proton donor. So that is the definition of Lorentz-Bronsted acid definition. Now, a base definition of Lorentz-Bronsted is said that an acid is a proton acceptor. That is a base definition of Lorentz-Bronsted. But if they ask Arrhenius acid definition, then you said an acid is a substance that produces hydrogen ion in an aqueous solution. That is an Arrhenius definition of an acid. Should they ask Arrhenius definition of a base, then you said a base is a substance that produces hydroxide ions in a solution. Yeah, so you must be able to define acid and a base according to Arrhenius and Bronsted. So let's look at 7.1.2. They said give a reason why ethanoic acid is classified as a weak acid. Why this ethanoic acid is classified as a weak acid. Okay, so let's look now at the table that I have written for you. So these are the strong acids. So in your exam guidelines, you are told that these are the strong acids that you must study for your acids and bases topic. The first one is the hydrochloric acid, then you have the sulfuric acid, then you have the nitric acid. So these ones are your strong acids. Why we call them strong acids? Because they ionize completely in a solution. So look at your weak acid. You have your oxalic acid, you have your phosphoric acid, you have your ethanoic acid, you have your carbonic acid. All of these are your weak acids. Why? Because they do not ionize completely in a solution. Then you look at your strong bases. A strong base is a substance that dissociates completely in a solution. For example, you have your sodium hydroxide, potassium hydroxide, magnesium hydroxide, calcium hydroxide. All of these are your strong bases, they dissociate completely in a solution. Now let's look at your weak bases. They are called weak bases because they do not dissociate completely in a solution. For example, sodium carbonate, calcium carbonate, sodium bicarbonate, and your ammonia. Now I put a star here. The ammonia does not dissociate in a solution. Unfortunately, it ionizes, but is also listed in one of the weak bases. So they asked us about this one. They asked us why the ethanoic acid is considered a weak acid. The reason is because it does not dissociate completely in it does not ionize completely in a solution. So we write that now in 7.2.1 because it does not ionize completely in a solution. Yeah, so that is the reason this one, or you can say in water if you want. So for 7.1.3, let's check now the following question. So 7.3.1, they says, write down a formula of two bases in the equation above. The formula of two bases in the equation above. Okay, so this is your equation. If you look at your equation, you can see that now this ethanoic acid on your left, it donated a proton. It donated a proton to the water, and the water became H3O plus, which is a hydronium ion. So this is an acid because it donates. So if you look on the right of your equation, it became this CH3COO minus. So we call this now the acid 1, and its conjugate base is CH3COO. We call it base 1. Now this water which received a proton, remember Bronsted says a base is a substance that accepts or receives a proton. So this one is our base. Then you look at the right, it became H3O. So we call this now base 2. We call this acid 2. So now this is the acid and this is the acid. But this is the base and this is the base. So the question then was asking, write down the formula of two bases in the equation above. So the two bases that we have, we said is the water and CH3COO. So the answer for this one, we say two bases is H2O and CH3COO minus. So these are the two bases in the equation above. So let's look at the following question. 7.1.4. Oh, sorry, we have 7.2. So in 7.2, now the statement says, a flask containing 300 cm³ of a dilute sodium hydroxide of a concentration of 0.167 moles per dm³. 7.2.1, calculate now the number of moles of this sodium hydroxide in the flask. Calculate the number of moles of this sodium hydroxide in the flask. So what they gave us here, they gave us a flask containing 300 cm³. Okay, so let's put all the details in the answer book. So what we have here, we have, let's write our data. So this is 7.2. So we have the volume. They said the volume is 300 cm³. Then they said, yeah, it has a concentration of 0.167 moles per dm³. So the concentration is 0.167 mole per dm cubed. So they said must find the number of moles. This is a sodium hydroxide. So first we need to convert now our volume from cm cubed to dm cubed. So we do that by dividing by 1000. So if you divide 300 by 1000, I think you're going to get 0.3. So just to confirm, you said 300 divided by 1000, so that will be 0.3. So the volume is 0.3 dm cubed. So you first convert the volume. Now, then we go to the formula to find the number of moles of the sodium hydroxide solution is C times V. Then the concentration is 0.167 multiplied by the volume, which is 0.3. So we multiply the two. We have 0.167 multiplied by 0.3. So the answer for the number of moles we get 0.0501. So 0.0501. You can say 0.05, it's fine. Number of moles. So that's what they require of us. So let's look at 7.2.2. So now they said now the ethanoic acid of a volume 500 cm cubed and unknown concentration. There's unknown concentration there. Unknown concentration X is now added to this flask to give the solution of volume 800 cm cubed. It is found out that the pH of the mixture is 11.4. The balance equation for the reaction is this one. So then they said calculate the concentration of the OH minus ion in the mixture. In other words, the concentration of the hydroxide ion in the mixture. Okay, let's explain what is happening here. Okay, yeah, you have a solution or you have a flask. This is your flask. So inside the flask, remember you had first the flask that was containing the sodium hydroxide, and the volume of that sodium hydroxide they said is 300 cm cubed. Then they said in the same flask now they added the ethanoic acid, which has a volume of 500 cm cubed. So that's why the volume now increased to 800 cm cubed. So what they told us now, the concentration of this ethanoic acid is unknown, but the pH of the mixture is found to be 11.4. So we know the pH of this mixture is 11.4. That is the pH of this solution. So they said now calculate the concentration of the OH ions in the mixture. Now this base, which is sodium hydroxide, is going to produce the OH ions, which is the hydroxide ions. This acid now is going to produce your hydrogen ions or your H3O ions. It's the same thing. The hydronium and the hydrogen ion is the same thing. So now we want the concentration of the OH ions, which means the ions that will be produced by the sodium hydroxide. So how are we going to do this one? Yeah, so this is your base. Your base, we know that the base dissociate. So it will dissociate to sodium ion and to hydroxide ion. Then we want the concentration of this one. The concentration of your OH ions, OH minus ions. Now the acid, which is ethanoic acid, will ionize to form this CH3COO minus, and it will form these ions in the solution, or sometimes they write them as H3O plus. It's the same thing. So now we need to check the formulas now that we can use. Remember, they told us the pH is 11.4. So let's look at the formulas for the pH. All right, in your data sheet at the back of your question paper, you will see this table. This is a formula table 2. So this is what we are required to find. We are required to find the concentration. The square bracket around that OH minus means concentration. So they mean concentration. That means we need to calculate now this OH minus, which is a concentration. But we don't know the concentration of the H3O plus, which is the concentration of the hydrogen ions. We know the ionization of water is 1 times 10 to the power negative 14. So we need a formula now to find this one. We can look above. Here is it. So this concentration of the H3O can be found by using this formula. pH is equal to negative log times the concentration of the acid. This is the concentration of the acid. This is the concentration of the base. So we are going to use this formula and this formula. So we want to find the concentration of the base. We need first to find the concentration of the acid. So we need to start with this formula because we know the pH. So we said we're going to use this one. pH is equals to the negative log times the concentration of the acid. Yeah, so we need to start with this one. So what is the pH? They said the pH is 11.4 equals to the negative log times the concentration of the acid. Then remember, this acid is CH3COO. It's a very weak acid. It's going to only ionize to form 1 proton in that solution. So we only have 1 proton. It's like you only have 1 H plus. It's only 1. So we only want 1 H plus ion. If inside here you had example a H2SO4, which is sulfuric acid, we know the sulfuric acid is a strong acid, but when it donates its 2 proton, it's going to remain as SO4 2 minus plus 2 protons, because it's got H2, so it's got 2 protons, so it's going to produce 2 protons. Then if we were required to find the concentration of the hydrogen ions of the sulfuric acid, here we were going to multiply it by 2. We are going to have 2 times of that. So the reason we only have 1 is because of our CH3COO only donates or only ionizes to form 1 proton. So you must be careful of that one. So it's fine. You can just put it as H3O plus. We know that is only 1 of it. So we want now to calculate this. Now, how are you going to do that? Remember, the log has a base of 10 according to your math. So let's divide all of this by negative log, which is a base of 10. We divide that side by the negative log, which is a base of 10. Then according to your mathematics, this is going to be equal to the base of 10 to the power negative 14. And this will cancel out, and then you will have the concentration of your H3O plus. Now we have this H3O, which is equals to 10 to the power negative 14. So you can actually calculate that on your calculator. You can say you have 10 to the power of negative 14. So you can see that it gives you 1 times 10 to the power negative 13. So it's 1 times 10 to the power negative 13. Okay. Oh, sorry, I think I made a mistake there. It's not 11, it's not 10 to the power negative 14, it's 10 to the power negative 11.4. Let's do that again. So it's, you have 10, let me write it here. You have 10 to the power negative 11.4. So when you press that in the calculator, put a 10, go to the power. So you say 10 to the power of, then you open the bracket, put a negative 11,4. You can say that is to the power of 11 to the negative 11 to the power 4. Then you said answer. Yeah, this is the correct answer. So the correct answer is 3.98. We can even take 3 decimals, it doesn't matter. You can say it's 3.981 times 10 to the power negative 12. So we can say the concentration of your acid is 3.981 times 10 to the power negative 12 mole per dm cubed. Yeah, so this is the concentration now of the acid or the proton in the solution, 3.981 times 10 to the power negative 12. Now we need to go and find the concentration of the base or the OH, the hydroxide ion in the solution. So we said we're going to use the formula, that is Kw equals to the concentration of the acid multiplied by the concentration of the base. So we want the concentration of this base, so we're going to use this formula. And the Kw, which is the ionization of water, is 1 times 10 to the power negative 14. So we're going to use this formula. Yeah, so this is the formula. The concentration of the acid multiplied by the concentration of the base gives us this ionization of water, which is Kw. So we know the concentration of the acid is this 3.981 times 10 to the power negative 12. So we put it here in the concentration for the acid. Now we are going to find now the concentration of the base. So what we'll do, we just divide everything on the left by 3.981 times 10 to the power negative 12. We also divide this side by 3.981 times 10 negative 12. Then these two will cancel. Then now we'll find the concentration of the hydroxide ions. So let's divide these two. So we have 1 times 10 to the power negative 14. Then we divide that by 3.981 times 10 to the power negative 12. Then we find the concentration of those to be 2.51 times 10 to the power negative 3. So it's 2.51 times 10 to the power negative 3 mole per dm cubed. Yeah, so that is how we calculate the concentration of those hydroxide ion in that solution. So let's look now at the following question. The last question now, the initial concentration X of the ethanoic acid. The initial concentration. Remember, we did not know the concentration of the CH3COO, the initial concentration. Now they require us to find that initial concentration. Okay, this is the simplified scenario of what is happening in this reaction. So this is your solution. You have that sodium hydroxide react with this ethanoic acid to form this substance, which is CH3COO, Na, and water. So in this mixture, now remember the question that we did previously, they were focusing at that mixture. When we added the 300 cm cubed to the 500 cm cubed, we got 800 cm cubed of the mixture. Remember, initially they said we must find the concentration of the OH, this concentration, the concentration of the OH ions. Now, these are the concentration of the base. So we did that calculation. We find that the concentration of the base is 2,51 times 10 to the negative 3 mole per dm cube. We were able to find this because we started by finding this, the concentration of the acid. We discovered that it was 3,98 times 10 negative 12 moles per dm cube. So this is what is happening inside the mixture. So let us focus again at that mixture, at the end product. What is inside that mixture is this. So, okay, I'll come back to this. Let us look at what we were given initially. They told us that initially the volume of the sodium hydroxide is 0,3 and the concentration was 0,167 mole per dm cubed. The volume of the acid is 0,5. So in this question, remember they asked us to find now the initial concentration of the acid. We want the initial concentration of the acid. In other words, if you divide this into 3 sections, like the first row is the initial, the second row is what was used or what reacted. You can actually also say here what reacted, and then this is what remains, or this is the end product. So this is the end product. So they said now we need to find the concentration of this acid here. Initially, what was the concentration of the acid? Remember, we don't know anything else, what reacted and what remains, what reacted, what remains. But we can use now the end product because this is the end product. This is this. So we can use now this end product to determine the number of moles of the base there. We can also determine the number of moles of the acid at the end product, which is what was in the mixture, what remains in the mixture. So we are going to use all the information we have in the mixture to find the number of moles of this that remained and the number of moles of this that remained. Then if we know the number of moles that remained and we know the number of moles initially, remember I think we did the calculation to find the number of moles initially of this. I think we discovered it to be, yeah, it was 0,0501 mole. This was the number of the sodium hydroxide initially. Number of moles initially, we do know is 0,0501. So we said it's 0,0501. So we do have the number of moles initially for the sodium hydroxide was 0,0501. So in order for us to be able now to find the concentration initially, remember the formula, the concentration is equals to N over V. That means we must know the number of moles initially for the CH3COOH. So we need to find now this number of moles. Remember the volume here is 0,5. So what we need now, we need to find this initial number of moles for the CH3COOH. Now to find the number of moles initially, we must know the number of moles of what is reacted or what was used. So let me use the term, the number of moles that was used. So if we can find the number of moles of what was used, and we can add it to the number of moles of what remains. Remember, this is like, imagine like you have an apple. Initially, this was your apple, and then you took a bite of your apple. This is what you used, or is what reacted. You consumed this one. And then now this is the apple remains. So if I ask you what was the apple initially, what was the mass of the apple or the grams of the apple initially? If I told you that what is remaining of the apple is 7 grams and what was consumed of the apple is 3 grams. So what was the apple initially? Then you can simply say the grams of the apple initially is what was used plus what has remained. So what was used is 3 grams. What remained is 7 grams. So 3 plus 7, that's 10 grams. So we know that the apple initially it was 10 grams. So in our reaction, therefore, we have to find what actually remained, what was used, then we add now what remained and what was used, then we'll be able to find what was initially. So here's a formula. The number of moles initially is equal to the number of moles that we used plus the number of moles of what remains. So this is what we are going to do. We are going to move like backwards. We will start with the end product, get what remained, and then we add these two, then we'll be able to get the number of moles initially. Remember, we want to find the concentration initially, so we need to know the number of moles initially divided by the volume. So the key now is that number of moles initially, which is dependent on the number of moles used plus the number of moles remaining. So that's what we are going to do. Yeah, look at the table again. So we need now this number of moles that was initially, but we need to find first the number of moles used and the number of moles remaining. If we can get this one and we can get this one, we will add these two number of moles to get the number of moles initially. Then we divide by the volume, then we'll get the concentration. So how are we going to get this number of moles that actually remains? So we know, therefore, the end product, we know the end product, we know what is in the mixture. Let's look now at the concentration. This is the concentration of the acid that we have and the concentration of the base that we have. So let's first find the number of moles of the acid. The number of moles of the acid, remember the acid now is this H3O+. So the number of moles there will be the concentration multiplied by the volume. So the concentration is 3.98 times 10 to the power negative 12 multiplied. The volume in the mixture is 800 grams, which we know if you divide by 1000 is going to give you 0.8. Okay, let's punch that in the calculator. So we have 3.98 times 10 to the power negative 12, then multiplied by 0.8. So we have the number of moles to be 3.184 times 10 to the power negative 12, 3.184. So this is 3.184 times 10 to the power negative 12 moles. So this is the number of moles of the acid in the mixture. We know now this is what we have here, the number of moles in the mixture is 3.184 times 10 to the power negative 12. So this is the number of moles remaining. So let's check now the number of moles remaining for the base now. Using the mixture again, the number of moles of the base is equals to concentration times volume. We know the concentration is 2.51. 2.51 times 10 to the power negative 3. The volume in that flask is 800, which is 800 cm cubed, which is 0.8 dm cubed. Now let's check this one now. The number of moles in the end product for the base is 2.51 times 10 to the power negative 3. Then the volume is 800 cm cubed, which is 0.8 dm cubed. So we have something like 2.008 times 10 to the power negative 3. So is 2.008 times 10 to the power negative 3 moles. So let's transfer that here. So we said, okay, we have 2.008 times 10 to the power negative 3. So we do have now the number of moles remaining for the base and the number of moles remaining for the acid. Now, we cannot simply get the number of moles used now because we don't know the number of moles initially. Let's first find the number of moles that were actually used or reacted for the base. Now, to find the number of moles reacted, so we'll say the number of moles initial minus the number of moles remaining. Imagine again, if let's say I ask you what is the number of moles that actually reacted used. If you know the number of moles initial and you know the number of moles remaining, then you're going to say the number of moles that we used is the number of moles initial minus the number of moles that were used. That actually remains. So this is the number of moles remains. So initially I had 10 grams of an apple. Then I find that it was 7 grams that was left. So I know that the number of moles that we used is 3 grams. So if you know initial and you know remaining, you just say initial subtract remaining, you know what was used. So that's what we are going to do here. So let's subtract the two. So we had initially with 0,0501 minus what we have remaining is 2,008 times 10 to the power negative 3. So we have something like 0,048. That's what was used for the base, 0,048 moles. So we have the moles here that was used to be 0,048 moles. So this is the number of moles that was used. Now to get the number of moles used now for the acid, we can just use our ratio. Look, we have the ratio 1:1 for the base and the acid. That means the number of moles here, if what was used is 0,048, then it would be equivalent to the number of moles used for the acid. It will also be 0,048 moles. So we use now the number of moles for the base to get the number of moles used for the acid. Now we do know the number of moles remaining. We do know the number of moles used. So we'll just go to add now these two to get the number of moles initially. So the number of moles initially will just add the two. So now let's add 0,048 plus 3,184 times 10 to the power negative 12. So it's still 0,048. So the number of moles that were actually initial here is 0,048. So I'm going to put that here. So it's 0,048. Yeah, so that's the number of moles initially. When you add what was used to what remained, you get 0,048. Now, the last answer, therefore, is to find now this concentration. Now we know the number of moles initial. We know the volume initial, 0.5. Let's divide these two now to get that concentration. So let's do it here. So I'm going to say now the concentration initial for that acid is equals to the number of moles initial divided by the volume. Okay, I'm not going to write the values because of space. Let me just say, so I have 0,048 divided by 0,5. Then I have my concentration as 0,096. So my concentration is 0,096 mole per dm cubed. Yeah, so that's the concentration initially for the CH3COH, for the acid. I hope this makes sense. We'll do more of these questions for it's called the stoichiometric calculations or titration calculations. So we have to do more of this, then you can get used to it, then you can understand what is going on. So I think that was a last question for the acids and bases. So I'll see you now in the next video for November 2021.
apart. I almost gave up till the loud voice said unto me, you're a child of the King, the great Master is He, who will keep you from falling and suffer defeat if you call on Him on your greatest time of need. Alpha and Omega, the beginning and the end.